Hey everyone! I don't have my introduction today. I figure those poor people who watch these videos and have to go through that long introduction and always get to the part where we start. Hello, I'm Dave the Hilster. You've reached Saturday Science Chats in the year 2022, which just doesn't sound right for we people of our age, but welcome. Yes, you have reached the Saturday Science Chat, sponsored by the John Chappell Natural Philosophy Society and Dissident Science. So we want to welcome everybody today. We've got a great show today. Yes, today we have the particle model. I've talked about this a lot. Some people say that's all I talk about, which isn't true. I know that, so we can throw that notion out. Just go back in our videos. But you will be joined. I will be joined by my father, Robert Hilster. And last year we launched our book on the particle model, and we'll be talking about that today. Actually, to be busted up into two talks. A very natural way for us to bust it up. Actually, my dad's working on a second book already on the particle model, but that's what we will be talking today. So you want to stay tuned. And of course, I want to thank all of you for all your support. I hit 4,000 subscribers, Dissident Science. I know I don't come out with those really nicely edited videos. Hopefully sometime I'll do that again. It's just a lot of work doing those. So I've opted to do more with the interview type and join up with the John Chappell organization and do things that a little less time consuming, because yes, we have our real jobs. We don't make a living at this. Being a critical thinker and going up against the establishment science is not an easy job, and it certainly doesn't pay well. So, but I do want to thank everybody who's a subscriber of the Dissident Science channel. Thank you so much for reaching 4,000 subscribers. And we're almost reaching 1,000 subscribers with the John Chappell Natural Philosophy YouTube channel. So I want to thank you all for your support. And of course, our mission here is to be an organization above all that promotes critical thinking without malice, that supports and publishes and promotes serious scientific work outside the mainstream, to provide a forum for being able to talk about that, and to provide a forum for presenting serious papers and theories without fear of censorship, and of course to be run by the members in its entirety. We do have websites if you haven't. If this is your first time here, the best one to go to is beyondmainstream.org. It's an online magazine for critical thinkers. It's written in a way that's easy for everybody to understand. There's not a whole lot of technical jargon there, but it talks about, wait a minute, there are problems in physics and cosmology. What are those? You can click on those and find out, hey, what's going on? What are the problems? And we also have a place where you can get involved with the community and support this organization. You can go to naturalphilosophy.org. Yes, we own that. We don't own naturalphilosophy.com because that was like thousands and thousands of dollars, but we did put our monies together and bought this domain name a while back, and we are, in my opinion, the best organization on the planet to be able to take care of the this domain name. Hey, good morning, Mr. Jesh. Nice to see you. And we do also have a Wikipedia. It is a true wiki software. It's exactly the same thing. And we have on that the Natural Philosophy Wikipedia. It is closed to the public. Why? Because Wikipedia is consensus. Anytime you even publish real data that is verifiable in the laboratory that goes against, for instance, relativity, they won't publish it. They'll call it, it is truly a consensus website, and this one isn't. So you're going to find over 10,000 pages of information about people working outside the mainstream. So those are, and again, I do want to thank all of our membership people who are members of the organization. We do have monthly and annual memberships. We have people who pay $5 a month. We have other people who pay us one time a year. We've got all of these categories, but we certainly need your support. I did a spreadsheet from 2021 for those who are members and paying supporting members. We are around $2,200 to $2,300 a year, and that's basically for websites, software that we use that is now subscription based. We have a server protector because we get hacked. We have backups, all this kind of stuff, because yes, for 5 years our server was on my server, we were hacked, and so all those things do cost money. And I do want to thank people for their generous donations. In fact, do want to thank Nick Percival, Dr. Cynthia Whitney Ramsey, it's his pen name, and of course all our annual and monthly memberships. But we need you. It's vital, your support. I wish I was a wealthy man, and of course I could do this even full time, but I can't. So we depend on our membership. So please consider, you can go to naturalphilosophy.org. Please consider becoming a member. It's not Patreon or anything like that. It's basically we have our own software, the membership software, which we have, and you can go right on there. And you don't have to remember. That is, you can hook it up to your bank account or whatever. Or if you do want to and you want to donate to us, just contact me, david@naturalphilosophy.org or david@thehilster.com, and we will be very happy to send you how you can send a check. Many people, more old-fashioned, will want to send a check. So I want to thank those patrons. And of course, coming in 2022, we do have invited guests. We're going to have some of the best of CNPS conference talks. A lot of people who don't know haven't seen some of the great talks given at our conferences. We're also going to have Dissident Science news takes. That is, we're going to take a look at just what's out there in the news and have so you can see what we critical thinkers think about when we see something like, multiple universes or multiverses and those kinds of things. So we're going to have some segments of that so we can keep more up to date. And we actually have debates too. I think I put those here. But we also have new historical perspectives in science that are coming up. We're going to have one the end of January on quantum mechanics. That is a critical thinker today, critical thinker who thinks outside the mainstream, giving us a history of quantum mechanics and what we think of it. So coming up next week, tomorrow, not tomorrow, next week, Robert D. Hilster is going to be giving a talk continuing on our particle model, the physicality of electronic circuits, including experimental support, predictions, and support for the model. That has been done. There's been 2 experiments done with the particle model in electrical engineering. Very shocking things. My dad is electrical engineer. And Eric Reeder will be giving a week after that the history of quantum mechanics. And of course, he has a lot of ideas of what's going on in quantum mechanics. Really great speaker. He spoke to us before, but he's going to be giving us an overall view of the history and how that fits in. We are going to have debates on special relativity, general relativity, dark matter, and more. I'm starting to talk with people. We are going to be meeting once a week, both the directorate once a week. Man, no, we're going to be meeting once a month, and the directorate to talk about the organization. We're going to get more organized this year, and since COVID's still ravaging, we're going to keep obviously do this virtually, and we're also going to have once a month open memberships. If you are a member, you can come in and we'll be talking about what we're going to be doing, and also people who want to be speakers and that kind of thing, and organizing the debates. So that's going to be great. And of course, we're going to have a history of general. We're going to also have history of general relativity, light, gravity, magnetism, electricity from a dissident point of view. So really great things coming. And I guess that is done for now. Let me just remove this from the flow. I'm going to bring up to the let's see here. Hold on, give me a second. Got to get, most people have production people doing this for us, but I'm going to bring up my father, and we're going to talk today about our book and the particle model, like I promised. So without further ado, I will bring up my dad and say hello. Let's see if we can hear you. Hello.
Hello. Got me? Yeah.
Yep, we got you. We got you.
And speaking of the book, this is
There it is.
my copy. I had to buy it for crying out loud. I don't get it. Right? You work hard to do these things, and you still pay for it. Oh well.
Oh yeah, well that's okay. I figured because we're going to talk about the particle model, I talk about it so much, people would be scared away. But no, we have people here, and I do want to thank everybody in the green room and everybody for coming by. But before we start, I want to talk to you, Dad, about not really the history about it, because I'm going to talk a little bit about that in our talk, but more about um, how what's been involved in the last 6 years we've been writing. You came up with this idea for light, but afterwards we had describe really the first year and a half of us working with the particle model. I mean, just as a scientist, emotionally, the whole thing.
Yeah. Well, that I had made the comment to you, Dave. It may have been more than a year had gone by. It had to be because I told you, I said, Dave, that was probably the most exciting, fun year that I've ever had working in science. I had just worked 10 years on gravity, grinding it out step at a time, looking at this, doing equations, calculations. Yeah, it was, that was interesting, and it gave a nice background for what happened next. But when I described to you the particle model for light, and you went ballistic, and I went, "What are you doing? Why are you jumping around crazy like?" And but after things settled down, I realized, wow, maybe this model for light is unique in that it's only particles. It has waves, but not in a classical sense. It has a wavelength, but anyway, then when I finally got into it, I got into it. I can tell you, I was it was a couple of weeks after that big discovery when I told you about the light. Mom and I came over. We were babysitting Lawanda, and we were sitting there and talking, and I hadn't done anything. And you started talking about something, and you got excited about what you were doing, and I'm thinking, wait a minute, again, what's happening here? So then I went back and started to work on it myself. Started with refraction, applying light to prisms and seeing what I could find out. Nominally things worked okay, and then I went to magnetics, and then I went to electrostatics. I had trouble with electrostatics. Dave had to pull me out and get me going. But then I did circuits, and it just flowed so easily. The model seemed to explain it. Granted, at a surface level, not going very deep, not proving anything, just how does it work? And I went through so many things that first year. It was just amazing how things worked out and just kept me going. So that first year was exciting. And I have to say that there have been times throughout this last 6 years when I'm looking at the electronics and I actually apply the particle model to electronics. I'm saying, wow, look at that. I never understood electronics that way. And especially when I got to the diode and was actually able to explain the IV curve of the diode with a feature that I knew was there but couldn't apply until I got to the diode and the transistor. And that was years later. It was amazing. That first year was just plain exciting because we just went through it at a surface level, making sure that it generally made sense, even though we didn't really have any details worked out.
Yeah, I mean, it really was exciting. I remember that year and a half. It was just like a kids in a candy shop. I mean, it was like someone first came up with, we came up with a rock and roll. No one wrote any songs in it, and we could just write anything. It was like new, but it was really exciting. I remember one time it was Christmas break, and you and Mom and I went up to Cape Canaveral, and I was trying to hack how color worked in, with your light model, when light waves would hit a surface and then how that would translate into some color, right? And, the whole idea of, light's transmitting of data, really, that's what it is. Waves transmit information. And I remember sitting there in the restaurant looking at the wall, trying to figure out and talking with you about it. It really was a magical time. And but it's been up and down as well. I mean, there have been times where I think it was, especially in the first number of years, there were days where I thought this can't be right. It's too simple. Yeah. And then and I would go through these crises constantly. In the day, I would say, "This is great. Oh, this isn't right. Oh, this is great." And it's not that the thing was failing. The problem was every time we thought it'd fail, we would end up coming up with a solution.
Yeah, but, there was my first look at dispersion, and I probably wrote a white paper on it, sent it to you, and I was off working on something else, and you dropped by and you stopped at my desk and you said, "Dad, this isn't right. The dispersion you hit here, that's not right." I said, "Yeah, it is." And so I get a piece of paper and I start drawing, and they start explaining, and then I stopped. I looked up at Dave and said, "You're right." This answer isn't right.
Yeah.
And dispersion took a long time to solve.
It did.
It took a long time. Yeah, you had the tools, you had the idea, you get a little piece. I had a little piece, you got a little piece. And over time, working together, that was the really good part of those 6 years, is being able to bounce ideas back.
Yeah, I mean, that's one of the things that I think people even who did reviews, and some of the people in our family who read the book had no idea what we were doing. I think one of the things that we found out was, that's very unique. Yeah, father and son team, all that kind of stuff. But to be able to have somebody to bounce things off, when you're by yourself writing, so many people have written really great. I mean, there's some really great models out there of the universe, atomic models and all that, but you don't have anybody to bounce something off of, and you don't have anybody on the same goal as you. And that's been quite amazing. So, all right, Dad, I'm going to bring you back, and we're going to, you're going to be there. I'm going to bring up our slides here. And we will start with our talk on Principia Mathematica 2, a complete toolkit for hacking the physical universe. And of course, my dad's here, and I told him he can chime in anytime, since, of course, it is written by both of us. But we got a lot to get through here. But we are going to give a book away today. And what we're going to be doing is you can basically say, describe the particle model. Now, you're not going to be able to do this until later, but you can either put that in chat, but you can't really do it now unless, of course, you already bought the book. But that's going to be our contest today. So once we're done presenting the particle model, and you want to put in the chat, contest : and then put your description of what the particle model is. My dad's going to be looking at them, and it's going to be totally my dad's subjective view. So if you want to bribe him, whatever you want to do to get him to, and I'm sure everybody's going to want this book because, the whole world's clamoring for, I'm kidding, of course, but we will be giving one paperback book signed by us, and we will send it to you anywhere in the world. I know we have some of the people here who have been following the particle model today. I want to say hello to Farouk. Farouk's there, Dad?
Yeah, hey, nice to see you.
Yeah, and he actually is in Morocco. We sent him a book, and we had a lot of people help us out with the book, so we sent it. And then, of course, we'll give 2 other ebooks away for the second and third prizes. So basically, contest is describe the particle model. Put that in the chat. So if you don't have the book, we're not going to send it to you if you have the book already. So anyways, I think that should be fun. All right, let's go on with the particle model here. So before we start, it was an interesting thing where I had a really big problem for the graphics because I am an artist. Yeah, it's a real artist. Go to dhilster.com. I am an artist. I paint. I have was represented by the Los Angeles County Museum of Art when I was in LA. So yeah, I'm an artist, so I want to make sure the graphics in our book. In fact, if you ask people, they say one of the great things about the book is you can visualize everything. You really almost don't have to read it. But one of the things I wanted to do was make these particles look as realistic as possible, because we believe, like Borkert, no two particles in the universe are the same. So I had this dilemma. So what I did is I wrote all these Adobe JavaScript programs, which are in GitHub. And those are the file names actually that you can run. And so it will generate all kinds of things in our particle model, from the loops, which is magnetic, to fields, to white light, to luminic wave. So everything you see here, all these things are literally unique particles. They are each drawn different. They have 1 to 3 tails. The tails are randomly drawn on them, so it's quite unique in the sense that the actual graphics in the books reflects the particle model in Borkert's. No two things are alike. We're going to talk about how we got into this. One of the things that, especially with people who know us, even who are friends and family, they go, "Why would David and Bob write a book?" I'm not a physicist. My dad, though, has a degree in engineering physics from the University up north. I'm just kidding. Michigan, University of Michigan. And so why do we...
Ohio's up north too when you're in Florida.
You're right. Okay, so I want to give a little timeline about how we got to where we did. In 1992, I met physicist Dr. Riccardo Carosani. His son-in-law walked into my wife's clothes store. She was a clothes designer, and I had some of my art on the wall. Said, and push comes to shove, and he goes, "Oh, Dave, you seem like a big thinker. Can you help my father-in-law get his work out?" And Carosani showed Einstein wrong back in the 1940s. He's got a PhD in physics in Argentina, and he helped ask to get the word out. He also showed the neutrino doesn't exist. And in fact, I think when I was working with him, he was my mentor in physics for quite a while. He actually found a paper by Buchner and Van de Graaff that was done at MIT in 1946 that clearly showed that the electron neutrino, which is of course the most important and it should exist, the neutrino doesn't exist. You can repeat that experiment today and show that in fact the electron neutrino does not exist. It was one of the other things of it. In 1994, 9 physicists from TRW, I showed them the work, could not, and what got me going in this is I took Carosani's work, and that was the beginning of the internet then, put it on the internet when you couldn't. It was very hard to do so in the early 1990s, but I was a computer scientist and research. And in 1994, I took his work and said, look, there's an experiment that Carosani suggests you can perform that will show special relativity incorrect. And so I sent that to the CEO of TRW, and I was in Space Park in the Artificial Intelligence Group. Next thing I knew, I was met from nine physicists from TRW. I gave them the information, and one of them took it away. And then three weeks later, I was hoping to get maybe they would do the experiment, but they said, we're not going to do the experiment, although we couldn't find a flaw in Carosani's explanation and of why special relativity is wrong. So that kept me going. 1996, this is how I got involved in this group. In fact, that top picture is from that year. I took Carosani's, I found through, I don't remember what, bulletin boards or whatever, the internet about this Natural Philosophy Alliance. I went to the conference in Flagstaff, Arizona. There I'm with one of the, can't remember his name, but he did an experiment, the guy in the very left, we're at the Grand Canyon. And he did an experiment showing special relativity is wrong using electronic equipment. Down here is the 2010 when we hosted it at Long Beach. And of course I met other dissidents, and I did actually share a room with John Chappell, and he was an amazing guy, but he was also kind of not great with money and stuff and needed some help. So I said, hey, yeah, we can share a room. So I got to meet John Chappell and be able to talk with him. And in 2004, as time went on, this is a friend of mine. I was working at a software company in Santa Monica, California. And this guy, who's a great guy, I love him. He's sort of a comedian, writer kind of guy in LA. He said, I told him, at work, I said, no one's paying attention to these scientists. He says, hey, Dave, make a film And so that's what I did. In 2006, Karazani, my mentor, pulled out of the film, which was very disappointing to me. And he asked me I said, Dad, can you help? And he said, yes, I can. So he helped with this experiment, which you see, which is in the film Einstein Wrong. You can go to einsteinwrong.com, see how you can watch it. Dad led the experiment. The experiment failed, but Dad came up with a new equation. There it is. It's basically a summation of all these small particles and forces. This is pretty simple. Zero. There's a 360. Oops. I think I should put in my.
Dave, that's you put up a really complicated one. You can start with a simpler one. That was complete for the time I did it. But
yeah, it's
believe it or not, that's just algebra.
Yeah, it is. It is, and it's basically the summation of forces. That's what it is. And of course, this was just a joke. My mom's sleeping. That's not my mom, really, but I mean, trying to be funny. And then Dad wants to quit in 2007. He said, "I'm done. I've worked on it. This is part of me in the filming when we were doing the experiment. I had a good photographer." He says, "I've done it." I said, "No, my film isn't finished." I was sort of worried about it. And then my dad continues, "Dad, you're still working on gravity." He says, "I know." And what kept him going was his equation that you saw, which was the preliminary form. It's much more simplified now. Had the graviton and Newton, you could see they were very close. And of course, if you look at a summation of small forces versus an empirical equation like the gravity equation for Newton, which is quite simple, it would pique your curiosity, and it certainly piqued my dad's curiosity, and that's why he continued. So in 2013, we finally launched. It took from 2005 to 2013 to film, 8 years, premiered in 2013 in Long Beach. I sent it to 80 film festivals. We almost made it into the Oxford Film Festival. Didn't get there because I had a person who was really interested and said, "Hey, I'm going to try to get this in," but they were really too worried about the controversy of a film called Einstein Wrong. You could have named it anything, but they have to watch the film, so you could say goodbye Einstein, hello Karazan, whatever it would be. Doesn't really matter, but it is currently available on demand. The reason it is that I did have an investment, I think about $150,000 altogether between my money and investors' money, and so we're going to play just for fun. The music video that I made. I had a friend composer, all great music. One of the great things about the movie is it has really great music in it. In fact, I get more comments a lot of times about the film. People say it's entertaining. They really love the music, and I actually had someone compose a theme song for a documentary about Einstein Wrong. I made a video that was sort of in 2007 to get used to the equipment, and I made this sort of short film. And it turns out that in 2012 and 2013, I took the music video written years later, put it on top of my short film, and it fit almost perfectly. It was almost a divine intervention or something. So we're going to take a look at that music video. It's a lot of fun, about 4 minutes long. Thought we would break up the history, and we'll get into the particle model after this. Here we go.
Every day I see a bright blue morning, the sun shining as the world wakes again. Hey mister, can you tell me, does space bend? All around you is the sound of laughter, joyous people celebrate a life so grand. Hey mister, read that fairy tale again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. A gentle breeze blows across the ocean, sending waves that crash upon the sand. Hey mister, did you watch Slow Down again? There is time for you to smell the flowers,
is out of this world. Step right up now, don't be shy, because we're about to show you how cars can fly.
Who dares to fight with the icon of his day, and she finds her own miracle on the way. I said, hey now, life's a joy. You gotta try your best and give your all, and when the facts don't fit the theory, change the facts again. Ooh, I've seen it, though you won't believe it. It's a miracle year in which we're living. Come on outside, it's a beautiful day. It's a beautiful day. Ooh, I've seen it, though you won't believe it. It's a miracle.
Okay, all right. We remember that, Dad, right? That was quite a lot of fun.
My gun didn't work. You gave me a gun, and the light didn't even come on. Come on.
Yeah, that's really true. It was one of the.
Gotta check the ammo before you do a heist, you know.
Actually, when we came out with that video, a lot of people were really quite upset about it, because they were, you know, the whole idea. I think a lot of people. It's funny because I pitched the film for my first investor, which was Ron Hatch, the guy who's the guy with the GPS, right? And I basically said I wanted to start the film this way, and it turned out I didn't start the film this way, because I actually had real editors who said don't do it that way, but it was still fun. But the idea was if we would kidnap Stephen Hawking and put a gun to his head and say, look, you know this stuff is garbage. You know this stuff isn't real. We know that relativity has problems. Let's stop this nonsense. And that's where it came from. But there were some people. I think he was still alive when this our video came out. But anyways, that was quite interesting. So let's get back to the particle model. I just thought that would be a lot of fun for people. Oh, I do want to say I want to thank you so much. We do have a person bribing us. We got a super chat. If those people who are on YouTube, thank you so much for super chat. That's basically you can send money, and it's a bribe for Bob.
You're very close to winning, I can tell you.
We should have done that. We were so stupid. We could, all the money, in this case, all the monies that you guys give go to the organization, the CMPS organization, to help pay for this. We don't take any of this. But anyways.
I don't care how much money you pay me. I will not falsify the test data.
Yes. But let's see. Anyways, it was pretty funny. We do have some people commenting on that. So thank you so much, Michael. That's greatly appreciated. It does go to help this channel continue and the great stuff that's going on. So let's keep going with our talk on our particle model here. So Dad will put this up here, and this is in the timeline, the place where our book started and the particle model started. Believe it or not, this was the diagram my dad talked to us, and this is a picture of the night he gave a talk to myself, my good friend from LexisNexis. He is a computer scientist as well from Brazil, and he actually knew a lot about physics and stuff, because he and I would sit at lunch time at LexisNexis and talk about physics, and he got really interested in it. So he's been a big supporter of the model. So my dad puts up this diagram of 1, 2, 3, 4, 5, 6, 7 dots with 1, 2, 4, 5, 4, 2, 1 on it. And I had no idea what that was, because I'm a visual person, and that's not a good picture. My dad did not. I did not get my drawing talents from my dad. It must have been from the generations from Holland, the great painters there. But no. But anyways, I saw that and I said, "That's incredible. You solved the wave-particle duality." It doesn't look like a solution to the wave-particle duality, folks, but it is. And I do have some Eureka moments. And before I get into the actual particle model, what that was all about, the Eureka moments are things that I collected over the years that have been what I thought really, really amazing things. Now, this is not like matters to anybody else, but to me they were. Yonel Deneu's underwater experiment simulating gravity? No! Okay, I'm sorry. I'm going to, let's see. Boom, 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 boom. I'm going to escape out of this and simulating magnetism. There we go. There we go. Magnetism, right? Is that right, Dad?
That's better. Yes.
That's better. Boy, I had to track that. I just do it on the fly here. I mean, it's
I
just
think there's hope for you yet.
not really. Most people have given up hope. So here's Yonel Deneu's underwater experiment simulating magnetism, Borchert's neo-mechanics and infinity. I remember when I read his book along with the it was called Universal Cycle Theory. I got him on the phone and I chewed his ear off for an hour and a half, saying how amazed I was at his infinite universe. And then Robert D. Hilster's solution for light, which we'll talk about in a minute. And then also last year, another Eureka moment is Jeff Yee's solution for atomic nuclei. And it blew my mind. These are other things. There was another thing that blew my mind, but it wasn't really impactful as much on the particle model, but we explained, which is mass increase for the expanding Earth. But the expanding Earth was also something that was really a Eureka moment. So this is our book, the Principia Mathematica 2. The cover for it. My wife said, "Oh, I like the cover." She hasn't read the book at all. She's not into science. Incredibly smart lady, but she knows my art, obviously, for many, many years. And she goes, "Oh, it's beautiful." I said, "Okay, I'll take that part of it, whether or not you agree with the science inside." But I apologize for people who do know this, obviously, but these videos are seen by lots of people who aren't like us, the uber nerds of physics and stuff. But a lot of questions we get even from friends and family. Why Principia Mathematica 2? Well, that's Principia Mathematica was wrote in 1687, basically translated. It was all in Latin. Mathematical Principles of Physics. And Dad, the book is unreadable, basically, right?
You got to really retrain yourself to think the way Newton thought.
Yeah.
It's amazing. I'm glad there's an English version. Even so.
Yeah, even so, with the English version, it's very hard to read. It's very hard to read. But what people in general, for those again who are not into this as much, he discovered gravity, apple falling from the tree scenario, all that, and he developed equations for velocity, acceleration, force, gravity, and the beginnings of calculus. The modern calculus actually was done. The stuff that we see today was done later, but he was really the genesis of that. Our Principia Mathematica 2. Why do we name it that? Well, we're giving physicality to the entire universe using Newton's mechanical forces described in the Principia Mathematica. There were some problems he had that, for instance, with light, that I think my dad solved, that Newton couldn't solve, didn't know how to solve that. All, of course, we're not comparing ourselves in any way, but I mean, we're talking about specific things, and all the forces are mechanical or Newtonian in our model, and all forces in the universe are caused by moving mass, and there are only 3 dimensions. So, but a lot of new, a lot of new models out there follow the same thing. Borchert's infinity model, infinite universe model theory is that way. Same thing. Jeff Yee's model, same thing. So, but all other models have magic. All of them. Borchert's model, even he doesn't talk really. He talks about things, but of course he hasn't fleshed them out. It could be that in the future, if he were to flesh out something more rigorous, like what we have done, that he could be a claim that it has no magic, he would say that. But again, I'm only talking about models that have been more fleshed out, much more detailed. The infinite universe theory is sort of more nebulous. It's an ether theory, which is okay. So we don't have charge. If you have charge in your model, it's magic. Elementary particle, that means a particle there's no smaller parts of it. In our opinion, that's magic. It just can't exist. You can't, if it's a case that it's all made of elementary particles, how do they use all these magical forces? They use magical forces to organize themselves, basically. Magnetic fields are talked about without any physicality. Electric fields are talked about without any physicality. Gravity is talked about without any physicality. And so is light. I didn't put those down, but I'm talking about more modern ones. And then, of course, many of them are overly complicated because they don't emphasize physicality. They get into a system. That system becomes a system that's not related to physicality, and it quickly goes away from that. So basically, if you look at the title of our book, the very top of that book says the universe is not magic. All forces are caused by something real. There it is. Let's see, can we do that way? Yep, there it is. So science still has no clue as to what stuff is. And that's, I think, the essence of what my father and I's book is about. From the beginning with Karazani back in the early 1990s and looking at all these great, all these great critical thinkers, I always was asking. People would talk about fields, and I go, what's a field? And they give me all the mathematics for it. I said, no, I want to know what the field is. And I never got answers to those kinds of things. Some of them I did. If you're a graviton, you have a gravitic field, etc. But that's what this book is about. There can't be anything in this model that's magic. It has to be all real. You have to be able to tell me or anybody on the street what light is, what magnetism is, all of those kinds of things. The entire universe. So that's the idea. So magic, magnetism, magnetic field is magic. We talk about it. Lionel Denis talks about it. He gives us some clues about it, but people talk about it. Even Jeff Yee, in his model, he talks about magnetism, even at the lower level in the subatomic area. Of course, gravity is an attraction. It's magic. Again, this is general kinds of things. This is not, a lot of people think about this a lot in our organizations. This is just more general for those people watching this. Electricity moves at the speed of light, but electrons go up meter per second. Current goes in one direction, electron goes in the other. We're going to get a lot into that next week because my dad will be is writing a book on using the particle model in the physics of electronic circuits. Light, it's a wave, it's a particle. What is it? And the particle model, what we call particles, is infinite. Again, Borchert's no partless parts, as you can see down here. No partless parts. So you have, I guess I'm going to have to get that back here. Laser pointer. Here you have beforehand, you've got electrons and protons. You've got quarks in Jeff Yee's model, which is subatomic particles, atoms, molecules, Earth, Moon, and Sun, solar system, galaxies, galaxy clusters, infinitely up and infinitely down. And particles, here are some particles, some electron clouds, here's some particles, here's a particle. In fact, Borchert says in his ether model that ether particles are like galaxies in his model, for instance. So that's one thing. And this is the entire model. That's why we have it on our book. That's why we have it on our t-shirts. This is on the front cover, and I thank Luis Sauerbaum from Brazil. He was one of the people who read our book, and he said, Dave, put that on the cover. And he's absolutely right. And actually, this is, the gravitic field. This is a magnetic field. This is the electric field, which is just basically flowing in one direction, and a lumitic field, which my dad added. And just to let you know, gravitic exists, magnetic, of course, we use all the time, electric, we use all the time. Lumitic is a word I came up with to fit all of this pattern. So yeah, I made that up. It doesn't exist except for in a particle model where it first came up. So gravity is the simplest thing. It's just particles moving in random directions. This is super old. 1690, Nicolas Fadio, Lesage in 1748 talked about this. So in our model, this is what we call the simplest classification of particle movement, and is the organizing one. Orbiting particles happen because of gravitic fields, and Lionel Denis showed that orbiting particles or things going and flowing in directions. This is magnetism. It just doesn't show anything if you've got to put more fields together, and that's where you get the attraction and repulsion. But this was shown in underwater experiments by Lionel Denis. So magnetism is simply orbiting particles. Question for those people who want to, in our contest, to describe the particle model: is a moon going around the Earth magnetic? if you want to answer that question in the comments, we'll let you know. And of course, this is I've shown this before, it's underwater experiments, but I did want to show just a picture of it. You can go and look under Yonel Denou, and you can watch this. I've shown this many times with those cylinders just go around. They go around in the same direction and in opposite directions. They cause a flow of the water around each one, and they'll either attract or repel, and they act identical to magnets. Not a little bit, but identical. And he actually has a second model that's even more involved. We'll talk more about that. I'm not going to show you that. Electricity, this is just me, sort of bounces off a little bit of some of my conversations with Glenn Borkert, which he said, well, it's just trapped ether in wires. Of course, there's a problem of how do you trap it. In fact, the etherists are working, in fact, Yonel Denou is an etherist, and he's having a heck of a time trying to keep his ether inside of wires and explain it. We do have a very easy way to do that. But regardless, we classify just simply movement of particles in the same direction, guided direction, doesn't matter, just in the same direction is what is called electricity. And we also then, of course, my dad in 2015, this is huge to me, is the first viable solution to the wave-particle duality, and that is particles come in waves. Now, I've heard people say, no, I sort of threw in someone, Roger wrote and sort of talked about it. There's going to be always the case where people have talked generally about stuff, but they haven't put it all together, they haven't understood it, they didn't look into it in any way. This is the first time, and when I saw it, I put it together with all those other kinds of things, and that's what we have. So those are the four classifications: light, magnetism, electricity, and gravity. And just to give you an idea of like waves of particles, these are waves. You can have frequencies of bombers, and you can have so you can measure frequency. In fact, it's funny that to think of a photon. A photon is not a viable solution because a photon's one particle. They don't talk about waves of photons. They never talk about that. In fact, Newton talked about the photon as wavelength being carried by the size of it or something. So you can look at this. There's another good way. I love this picture. This is gravity and this is light. Gravity is just your shower on normal, which are random drops. Light is when you put it on massage. That's it. And, okay, this is something I came up with myself, and it was hard for us to swallow in the beginning, but anyways, what we thought about is if something travels at the same speed, it's got to be the same particle. The question is, how could different particles travel at the same speed in nature? Answer, they can't. They must be the same particle. Conclusion, all particles that travel at the speed of light must be the same particle. That's where our particle model comes in. Now, I know there's going to be a dispute on this, but we have an answer for you. And during a solar eclipse, you have light and gravity seemingly coming to the Earth at the same time. Now, there's actually another experiment that my father found that is much better than that just measures the tides, very different. We're going to show you that reference. So yes, in general, if you ask the mainstream science, how fast is gravity, they'll say it travels at the speed of light. We agree with that. We've seen various experiments that would show this. Then, of course, there's particle accelerators. How about magnetic fields? Well, what do we use? We use magnetic fields to accelerate particles in particle accelerators. To what? The speed of light. So magnetic fields must be traveling at the speed of light. Electronic circuit, we know that travels close to the speed of light. So again, if they're all traveling at the speed of light, gravity, magnetic fields, and electricity must be the same particle. And you think that's absurd until you start working at it. And unfortunately, or fortunately, it works out pretty darn well. So, yep, same particle makes up light, gravity, magnetism, electricity. And we just lost all CMPM members. That's just a joke there because, I know everybody's etherist here. I know there was some objections to this. We're going to talk about it. You notice I did not put that our particle, the G1 particle we call it, is the electron. It's not the electron. Here's a question. I can give you the answer. The answer is the G2 field. So answer to what causes speed of light limit in your model is that there are infinite levels, and for a G1 particle to orbit an atom, for instance, what makes curving, well, you'll see what makes orbits is a gravitic field. There's a second gravitic field of particles going way faster than the speed of light, and that constant hitting of the speed of light is when a G1 particle, what some people would call an electron, we think it's a lot more than one particle, gets released. It's going to go at the speed of light. It's because of the G2 field below that. Where does that speed come from? The G3 field below that, et cetera, et cetera, et cetera. So good question. All right, here's the speed of gravity. Observational evidences for the speed of gravity based on Earth tide. This is an it's there double, but I won't pronounce the names. They're Chinese scientists. And this is what they said. We have found that the current practical Newtonian formula for gravity tide of the Earth implies a hypothesis that gravity travels at the speed of light. Furthermore, we have derived and solved the propagation equation of gravity using observational data of Earth tides from Shikwani and Washui. That must be two authors. After correction of the phase lag due to the elasticity of the Earth, we found that the speeds of gravity are from 0.93 to 1.05 times the speed of light with a relative error of 5%. This provides the first strong evidence to show that the speed of gravity is the same as the speed of light. So that's the one we use. Now we call this particle, we don't call it an electron, we don't call it a photon, we don't call it a graviton, we call it a G1 particle. G is for gravity. We say that that's the principal organization or the organizer for everything in the universe that makes things orbit, makes magnetism happen and all that. We have one for the level 1 of the universe because there are more than one, and we'll show you that with Coulomb's law. It just screams that there's a second gravity. G1 is responsible for what's commonly known for light, gravity, blah, blah. So we call it the G1 particle. There can be light, gravity, blah, 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 and there can be light, gravity, magnetism, and electricity movements at all levels of the universe. We're going to show you that too. What makes this model really great is that during these 6 years when we were hacking the universe, we weren't using equations. We were using a mind's eye. We know that gravitic fields cause things to come together. Gravity, which is falling objects, collisions basically, brings things together. Also causes curved paths. It also causes Earth's orbits. That is, if you were to throw this apple really, really, really hard, it would end up orbiting. And of course, there's even more complex paths. Of course, what we call electrons, or what we call lots of G1 particles flowing around nucleons in a G2 field. This is the same thing. So these are the intuitions we use, and we've been hacking the universe. In our model, we have not sat down and wrote equations to hack anything. It's all been visualization. So again, for those who don't know, I know there's going to be a lot of people in the CMPS know this, but I apologize. We do have a lot of people who don't know it. So particles in random direction, of course, gravity, how does that work? This is actually, again, my computer program that put together, well, not this one, this is drawn, but you can see that if you have these things going in all directions, fewer impacts, more impacts. We know that gravity travels through, if you believe in this kind of gravitic field, that it goes through matter. It's not all blocked out, but some of it is blocked out. And this is an actual computer plot where I took lines and I generated randomly using Adobe JavaScript. And you can see these circles are represented by squares, and each square then was used to do calculations of loss. So you can see, if you kind of squint your eyes, that the middle has less there, and this is called the shadowing effect. This is computer generated. I wrote the program for it. And people say, oh, the graviton, you can't have a gravitonic model because it heats up matter. No, it doesn't. G1 gravity is a random thing. It's sort of pushing on it and equal. It doesn't cause any kinds of oscillations, whereas a luminic light wave comes in and sort of boom, 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 and sets up the hits the nucleons and causes that in its G2 field to start creating oscillations. And of course, what makes heat is getting matter into these oscillations, and that's just that's happening. So no, gravity, of course, doesn't heat up matter, but that's one of the objections to gravitons. Two gravities. What's our first clue that there are actually gravity, that G1 particles exist and G2 particle exists? That is random particles at different levels of the universe. Well, you have a comet or planets going around, and you have G1 gravitic field that makes a planet go around, or comet curve around. Well, if you go down one level and you make the atomic nucleus and you have a G1 particle, and it's going around. It's again, this is not a one-to-one thing. I'll talk about that a little later. G1 particle is not the electron. I just put it there just for a reference point in mainstream. And you have the same kind of thing. A G1 particle will actually, like electricity, flows in and around the nucleons and the clouds of G1 particles around nucleons of copper. It sets up, actually, we can explain for not the first time, but at least we haven't seen an explanation for the right-hand rule. My dad's going to be talking about that next week. And so you can see that what the only difference is that on this side, on the right side, these particles you see are G2 particles. The bigger particle is the G1 particle. Up here you have the, now you can say that if you have galaxies moving in random directions, that's going to set up a gravitic field for some huge level things going on at higher levels, which we'll not be able to see, because if we were at the atomic level, we're not going to see a chair. So, is there any proof that, is there any indications, because there's never proof for anything, but are there any clues that this could be true? Absolutely. Take a look at Newton's gravity equation and Coulomb's atomic equation for the force. They look identical, and the only difference is that these are charges. So that's a big clue. And if they are in fact both gravitic, then what we would say is, oh, it's just a gravity 2 at a lower level. The particles are G2 particles, so you'll have a G2 gravity constant, and that the M2, so that when you look at the weight, I know, Dad, this is something that's you talked about a lot. You, in our model, you do not look at an electron and say what its weight is in regular, like kilos, right?
Right.
So basically, because a G1 particle is involved in making the weight, so
the G1 gravity, when it acts with another G1 particle, only acts on a collision basis. It can't act gravitationally. Theoretically, if you could have an instrument to do this, you would. There's no way to weigh a G1 particle against a G1 particle, because it acts as a collision. And the collision is by itself, is not gravity. So the G2 particle we show there has to have a different mass level. Right. It has to have a whole new definition, which hasn't been defined yet.
Right. Absolutely. And then, of course, we have a logo. I mean, every theory has a logo, right? That's so funny. I don't even know what to say about this, but I came up with a logo, and I thought it was pretty good. My dad loves it, and I do love it too. And then it actually stands for two things: Gravity 1 and Gravity 2. That's why you see that. And then Principia 1 and Principia 2. So let's talk about light. We're going to get into the more nitty-gritty now of our model. Of course, our book is way more detailed than this, but light, this is probably one of the most fascinating journeys we had. So the very first top here is the original drawing my dad showed to me. Then when he explained it finally, what it was, I got it. So I this is what he gave me. This is what he's really saying, that there's one particle, 2, then 3, then 5, then 4, 1, 2, 4, 5, 4, 2, and 1. And then I came up with even more realistic drawing using a computer program where every particle is different. You can see you can't find any two identical particles here. And you can see that the waves are not perfect and all that, but this would be considered a realistic, messy wave in light. Now, the question is then, how do you make white light? So my dad said, well, white light must be made of the RGB, red, green, blue, and it's all sort of all together, all there mixed. And that makes kind of sense in the evolution. So we're showing you our hacking of the universe using our model, and we're showing you the steps we went through. So this was one of the first ideas he had. I actually made a program just to do this, even though this isn't the way white light really works. But you can see that that's the idea, the sort of random, different sizes, all the different colors together. Again, computer generated to make it look, what would be sort of realistic. So I said, well, those are just lines. My dad is into art, so I'm going to change that into my computer program. And I'm looking at that and I go, okay, this is it. And then something when I watched it hit me, and it hit me like a ton of bricks. And that when I saw it, I saw in reality this. And so what white light in our model are basically, groups of G1 particles, or white light can be at any level, but in our level called G1 particles, groups of particles that are coming, and all the wavelengths are in there, but they get reflected off surfaces in different ways. So then you'll see a wavelength in general off of the nucleons of a certain surface, that kind of thing. But this is probably one of the more interesting ways you can see my father and I hacking what white light is according to our model.
Dave, it was
yeah.
interesting. The reason I came up with the model for light was that I had asked the question, how do I make light out of a particle? And it didn't work. I took one particle and I said, well, how can I make white light out of one particle? I said, just can't do it. The point being, simple point being, is white light was my basis for a validity of any form of light. It had to be able to do white light. And yet it took us 5 years from the time I said it in 2015 to the time in 2020 when you came up with that drawing. 5 years for me to get from one particle that can't be white light to that drawing. Quite amazing to take that long to do.
Yeah. So yeah, it was a triumph, really, in the sense of our model. Whether this is all correct or not. Of course, that's going to be none of you here are going to tell us it's wrong or right. What's going to happen is history is going to eventually tell us in one way or another. So here are some other things. These are older ones where they're much more less realistic. These are things I did before I had the computer drawing them. So basically, you can see here light in waves in a much more, how do you say, super sine wave, all going in a direction, of course. Reflection, of course, is just them bouncing off. Transparent is where the waves go through intact. In fact, nucleons and their positions are like, nucleons are like suns and all those things. And if you shoot a comet through it, it's going to either unscramble it or let it go all the way through. Translucent gets some of those kinds of things through. Opaque, this is the interesting one. So if you have waves of particles, why is it that when you are inside a cave, the G1 particles that flow through, gravity is flowing through, but light isn't? It's because the nucleons of atoms, the G1 particles that go through, are coming in organized waves, but because of the way the nucleons are, again, think of these as suns, and that a G1 particle is like a comet, it's going to unscramble it. So by the time it gets to you, it's unscrambled, and we don't see anything. Mirrored, of course, is all things, and polarized light is actually, I don't think it's exactly this, but polarized light we can explain in our model, and we do explain that in our book. I'm not going to get into it. You're going to have to buy the book. We can't tell you everything. So laser is really interesting. Just concentrate on this one part where the red ones are here. The problem with a ether model is a laser. You can't describe a laser. Everybody who has an ether model, you have to describe a laser. How is it that we can send a beam that's a very small beam and gets to the moon? Yeah, it spreads out a little bit to the moon, a couple miles worth, but lasers go in a very straight line. You don't have sound being directed. That is, I can't make my sound go to you and only stay in this kind of place. So our model describes of obviously lasers quite easily. This is just us hacking the laser, how it works. So the particle model has no problems with light going in lines, laser kind of lines, whereas of course, Try to make a wave in the ocean goes just 1 foot wide and just stay that way through the medium. Ether models can't do that. G2 gravity, we've used to, of course, it's Coulomb's force is really G2 gravity. That's what it is. Transparency that you versus opaqueness, and that's the G2 gravity, how light can travel through mass. Dispersion, something we haven't tacked. If you want to use our model and get the answer for dispersion, in our book we talk about it. My dad and I have not. Oh no, not dispersion. Dispersion we have. Diffraction we haven't. We don't have a satisfactory answer to it. And atomic polarity, really, really important. G2 gravity talks about that. And also in electronic circuits. But there's lots and more that it does. This is probably one of the more amazing hacks of our model. And when my dad and I were talking about dispersion, what is dispersion? Rainbows. Well, the problem is why does a rectangular prism not make a rainbow and a triangular one does? And the big thing that I told my dad, I said the only difference there is you have is the shape. And what does that shape do? Well, imagine you have a gigantic, humongous prism versus a humongous rectangle prism in space. Well, the gravity at the end of that tip is way less than the gravity near the end because there's more mass there. Gravity doesn't work as a point mass. We know that because if it was true, then we wouldn't have to do all these calculations even when we're sending something to the moon. So we know that there's a diminishing gravity there, and we know that because light bends, G1 particles bend because of why? G2 gravity. It's Coulomb's law, but it's just G2 gravity. It's just smaller particles moving faster at a smaller level. And because of this gradient of diminishing G2 gravity, what happens is the white light waves, you're going to get more waves in the beginning and less waves in the end. And guess what? That's exactly what happens. The more waves you get blue into the less waves you get red. And hack is done. Took us many, many years for that. The magnetism, we'll talk about that now. We talked light. Magnetism is, I sort of gave it the name called the Denew effect because we don't believe that magnetism actually works exactly the same as water, because magnetism isn't a liquid that's being pushed down by gravitational force. In the case of magnetism, it's just particles going around and around, so that's why I call it the effect. And basically, it's named after Denew, a scientist, a Romanian scientist who happens to live, I think, in Thailand. He's actually working on his ether theory, and he's got his model. Orbiting particles are magnetic fields. Orbits that clash repel. Orbits in the same direction attract. Again, we've modified a little bit. This is the underwater experiment. Again, it's not the same because you have water there and the gravity is pushing down on it, but this is how he sets it up. He's got spinning cylinders. When they are in the same in opposite directions, means the flows are in the same. Those cylinders are pushed together by a pressure difference. Over here, you have disturbances when they are the same. They're different, same direction, the spinning, but the flows clash. You get disturbances, and that pushes these away. He explains it by pressure differences. You can also explain it by G2 gravity pushing on the nucleons. So this is the way we look at the Denew effect. You have a disturbance when you have things flowing in opposite directions in meeting, whereas you have reinforcement. And when you have reinforcement, things get really stable. When you have repulsion, things, and that's part of the attraction. And it's only one way attraction and repulsion happen. Gravity also, gravity does attraction, but not repulsion. So at the atomic level, a couple of things. There's more than one G1 particle for each electron. We don't believe there's a one-to-one correspondence. And the idea that there's only one particle around a hydrogen atom, if you really go and look at the electron and look at all experiments done, there's really no definitive experiment that shows that an electron is really only one particle. We would say it's more of a quanta of particles that are held by a nucleon. So a hydrogen will hold so many. How many they are and what size, we have no idea. There's no charge. There's nucleon. There's no proton, so there's no charge there. And stability and instability of atomic structures involves the synchronization via the Denew effect. What does that mean? Well, again, this is a standard model. This is an exaggerated model, folks. This is just all symbolic. In our model, there's one electron. In standard model, there's one electron, one proton, for instance, in hydrogen. And where we have the particle model, we're going to have more than that. We don't know how many. What happens then are you have these flows that are set up. I'm going to talk about how those probably work. And you have all these flowing G1 particles, and they can even flow around. Remember, this is like gravity, okay? There's nucleons are like suns, G1 particles are like planets or whatever, and then you have G1 particles that act like comets. We know all these things exist in the gravity world. It can happen down at that same level. And what keeps these things together or apart are the flows. If there are reinforcing flows, that is the Denew effect, the magnetic kind of effect, the flow of flows in these atoms are going to have a particular flow, and those flows are going to set up reinforcing repulsions and attractions, and those things will be set up in a way that that's why we have stability or not stability. That's why we can have static electricity. You disturb some of these G1 particles, they stay around, they get around, and eventually they go back into the atomic structure, and those set up Denew fields or magnetic fields, and that is what makes things attract and repulse. Now, this is where the last part of is Yi nucleus. He's talking about not only the nucleons, and he is also the same. He doesn't call them, he maybe call them protons, but they're not charged. He doesn't call them charged, I don't think. He just calls them that, so, And he's looking at the arrangements of these things, really brilliant. And then he also has a proton being made of quarks. He then has set up physical models where he sets up magnetic fields and Coulomb's fields to what then it shows that the electrons, what we call G1 particles, are kept in orbit in the SPDF orbitals. Now, what we would say is that in Jeff Yee's models, giving us the first inklings of magnetic fields in the G2 level. And what those do is that keeps these G1 particles flowing in these SPDF orbitals. And he has modeled that. The difference between his model and ours is we're a particle model. He's an ether model. And we think there's a lot of problems with that. But regardless, this is brilliant, brilliant, brilliant work. And it was the first inkling that we have of how Hack 4 could happen, because our book is about Hack 3. And so that's amazing. And that would keep the G1 particles, the electron clouds, SPDF orbitals, those things that would have a certain flow to them. Those flows would set up magnetic fields, basically the Denew effect, which keep things apart or attracted. They get stable. Some of these are unstable. The reason we have things like radioactivity is the stable and unstableness of atomic structures, and that's the model that we have. The synchronization, because these things go at an immense speed, the amount of orbits you have an G1 particle, the cloud that we see is going so ridiculously fast. Imagine how many, I think it's 5 quintillion orbits a second around a nucleon if you're going at the speed of light. And what happens is we know for a fact that there's a thing called synchronization in gravity. Around Jupiter, you have Europa going 1 time, Ganymede going 2 times, and Io 4 times. And that is fixed. How does it happen? It's called synchronization. There's a great video on synchronization in general. It happens all over the universe. This kind of orbiting, you're going to get synchronization of these G1 clouds around the nucleon because of the G2 field, G2 magnetic fields, and the synchronization is what keeps things very stable. So now we're going to give a hacking demonstration of our model in something that I used for when we gave our talk The idea is, how do you hack a wireless charger with your phone using our model? And it basically has pretty much, it has everything in it, I believe. All of our four classification of movement. Electricity in a wire is just basically, my dad's going to talk about that. Copper nucleons are arranged such that G1 particles that are flowing around them, just like suns and comets, cause them to actually start spiraling. But regardless, the electricity is basically just G1s, like comets going through a maze of nucleons. And so that's the electricity from the wall. At that point, the electricity goes into the coil. That is just the G1 start flowing around the coil, because again, the nucleons are set up like sort of funnels for these things. That's the difference between our model and yes, some of them go out. We know that. Even electronics, we know that. They don't all just stay in perfectly, but most of them will. And then that sets up a magnetic field. This is a super simplification, folks. This is not a one-to-one. This is symbolic, but basically when you send G1 particles through copper wire, it starts to not only go through, but some of them start to go in spirals. Those spirals go outside the wire, so you actually have G1 particles guided by a wire, and they're not inside the wire, they're outside the wire. That causes these sort of flows going, and so that's why you have electricity. What do they say, Dad? It's induces, that the current induces current.
Induction is one of the magic words.
Yeah.
Because they never explain what the physical thing is really, and then how current in the coil at the bottom somehow generates a magnetic field, which they don't say what the magnetic field is either. But one current induces magnetism. Magnetism induces current. How? What does induce mean? It's a magic word.
Induction, induce is the magic word for sure. Again, this happens in our model. This is not the way it is. To do it more precisely, it's not the point here. The point is to show the model in general. In fact, we gave this test to people at our book signing, which were people that were not in the CMPS, who never talk or care about physics at all, and many of them got how to hack this using our model in the four movements. Of course, if you have those, the electricity, the G1 particles goes into the phone. This idea that somehow it magically something magical, it's not. The G1 particles are starting to be guided, and they're staying around the copper wires, but they are now flowing outside, just like if you were to have a bunch of suns together that were in a lattice and you would send them, you're going to have some comets that are going to still stay around them and keep moving, that kind of thing. And so that's how that goes. And so, some of those G1 particles get caught up into the lattice of the nucleons in the phone. At that point, the electricity is stored in the battery. It's another mystery. They do say electrons, right? But of course, current is the holes left behind electrons move. Hey, don't even. That's, my dad's going to talk about that. It's just a mess. But the G1 particles are, of course, captured in these atomic structures that are very good at capturing G1s. That's why we make batteries out of certain things. Their atomic structure is very good at capturing extra ones and holding on to them. And then finally, you do get lumitic waves, because those G1 particles in the battery then get spewed out into an LCD, which sends them out in waves to your eyeball. Now, it was really, really hard in the beginning for me to believe that these little particles are moving like this, and that a particle is from your phone is being sent to your eye, and it used to be inside the battery. But again, if you just think of what's really happening there's energy, we call, which is a concept. It's not real. It's being stored in the battery, and that energy supplies energy, electricity, to the screen, which then emits a photon. Of course, the idea that a photon is emitted, and we don't know what a photon is, an electron goes up and it goes down in a photon, it's not explained. Our model explains it. My dad will be talking about circuits. That's why we're not focusing this week on electricity or electronic circuits, because the that's going to be a whole nother talk. So we are it's 11:20. I'm sure I see lots of comments about ether, and that's what I figured. So that's why I don't think we're going to be necessarily having people jump on our bandwagon from this group. But I would say that we're going to have another talk. We didn't want to take up too much time, but so we can have some discussions and some questions. But TPN explains the left-hand rule or the right-hand rule. It doesn't matter which one you call it. You can use either one. That is the right-hand rule in electronics. TPN explains current through a wire and the resulting magnetic field. TPN has been applied to electronic circuits. That's going to be next week's talk by my dad. TPN is the particle model. Has revealed how wires, resistors, capacitors, transistors, diodes, batteries could work physically. Interesting point. I'll get to that. The last point here is TMP predictions for electronic circuits have been verified experimentally. It's not proof. There's never proof, but some predictions were made that were never observed in circuits. My dad did experiments with that. Next week, I'm going to get a little camera. I'll use my phone and hook up to this to show, so my dad can maybe show the experimental setup he has. It's really very complicated. A power supply and 3 resistors. Whoa! But it's really interesting. One of the things that is new to the model is that G1 particles are not at the speed of light all the time, especially in a circuit. They can actually speed up and slow down, right, Dad?
Yeah, I'm sorry, I was checking the chat list. In fact, a couple of people have asked questions about the speed of the G1, speed of light. What limits it? Can it go faster or slower, and so on? I think along with the ether, we need to let these people bring up their questions and respond.
Okay, that's fine. Absolutely, we will, because we were at 11:20, so we got 40 minutes. So let me finish the slides here. Some of the conclusions. There's one more slide. That's why I put up there, because I thought, okay. In our model, there is no magic. We don't have like a field, a charge, a plus, a minus, sitting there that does something. We don't have a elementary particle that is indivisible. We are very Borkian on that. The entire universe can be described by 4 particle movements. You notice that one of those movements was not ether. We're going to talk about that, I'm sure, because there are so many people who are etherists. I've never been an etherist, and it's funny because I've seen, I know about ether models for decades and decades and decades. And I went, yeah, because there were too many problems. Because I hung out with the MPA where these problems were given to people, and some of them, in my opinion, are very damning to ether. But it's okay. We don't have, in the classification, so we do not have ether. We do not have particles that sit still and have collisions. Okay, they're moving a little bit. They're moving back and forth all the time. Yes, but somehow they're sort of staying in the same place. That to us is a very rare kind of thing in the universe. And then all movements can be found at all levels of the universe. That is, all these, gravitic fields, lumitic fields, magnetic fields, electric flows, in this case, are found at all levels of the universe. This is the first model to describe everything in the universe as moving mass and entirely physical in a detailed way. Borkert does talk about that, but there's just not a lot of details there. So, if someone reads it, they're going to sit there. And he's trying to solve light and gravity. He says he has solved it. Yes and no. He also says, we're going to talk about that. And there are a lot of hacking still to do. Diffraction is something we really have not completely solved. We know sort of how it should work, but we haven't solved that. And in the universe hack 4.0, the atom, wow, not easy, but very interesting. And there is one more slide, and this is what I would come up with. My phrase, if I wanted to win the book, and that's what our contest is, of course. Let me put that up there. The contest is put contest colon and describe the particle model, and we're going to choose the best 3. First one gets our autograph book sent to them anywhere on planet Earth, and then we will also, the other 2 will get ebooks. Of course, you can buy the book online anywhere in the world on Amazon. I think it's on all continents. And go ahead.
Yeah, Dave, I've watched the comments, and nobody has come up with this, and that's okay. But if you are going to do it, the thing is, you need to do it now, or you're going to have to send me an email or something with your definition, because I'm looking to copy your comment and paste it into a group so I can compare them. But I haven't seen any so far.
Mm-hmm. Right. No, it shouldn't be. I told them not to. How could they talk about the particle model if they don't know what the particle model is? We've had our book out, and I know few people in our group have gotten it or read it. It's sort of weird. I know the people have, but very few. It's weird because when somebody has a book from our group that has a new model, I get it and I read it through cover to cover. But anyways, the idea here with this last slide is, this is my definition. This particle model is essentially a Turing machine for the universe. It means you're going to be able to describe everything as moving mass in some way, right or wrong, in some way. And that you can actually have more than one hack using the particle model for the same phenomenon. But it forces you to make everything moving mass. So anyways, that is it for us. We can, again, if you want to win our book, you can just describe the particle model, put contest, and then you can also then send an email to us as well. We'll choose the best ones and let everybody know next week. So I know there's going to be a ton of questions and comments and laughter and all that. So let me get this away, and let's bring up somebody.
Since I brought it up, MC, yes. I don't know who MC is. I think is ask a couple of questions.
Yeah, what we're going to do is we're going to go first to our green room, all right? And then we'll get to the comments as well. I think
that's there too.
Yeah, so you can star those. Do you know you can star those? Can you star them, Dan?
No, you haven't set me up for that. I'm not one of
no, that I think that's just when you're the moderator. So
yes,
we're gonna bring in some people from the green room. At least I know one person's hand's up there. We're gonna do that, and then of course we'll be getting to all the questions in the chat. And I'm sure one of the things is people are gonna want to know maybe why. I don't think ether is a good model, and tell you why. But as I'm sure other people who do believe ether are gonna. But we're gonna try to stick to the particle model, just like when we have anybody's model. But we can discuss ether if you want on that sense. Okay. Bob Gray, how are you?
Fine, thank you. Thanks for that presentation. Couple of questions and then a suggestion for next week. My question is, I want to make absolutely clear I understand. The G1 particle interacts with another G1 particle. It bounces off. It does not go through as like a hypothetical photon can go through other photons.
It has to be smaller to go through.
Okay, so does the G1 particles carry any momentum? So if the G1 particle interacts with another G1 particle or a collection of G1 particles like an electron or any other particle with mass, does the G1 momentum gets transferred to that other particle, or
there's no electrons in ours? We only have the two particles right now. The G1 will interact with itself, or it will interact with the nucleon. There is no electron.
Mm-hmm.
But
go ahead,
it carries momentum, but not in the classical level 1 sense where the momentum is mass times velocity and mass is in kilograms.
Right.
The G1, since it can't be measured by G1 gravity because it only collides, gravitationally you have to be able to pass through and sense that's how it senses the whole object, is because the G1 is passing through my body. G1 can't pass through it, so you can't measure it gravitationally. So it has a mass, but it's not kilograms. You have to define a new standard. Mm-hmm. A de facto standard I'm using is that 1 unit of G2 mass is the G1. the nucleon, the N1, is maybe 2,000 G1s, in a sense, stuck together. And so the G1 can hit the N1. They collide because they're kind of the same structure, the same thing. G1 can't really go through the N1. So they collide. They both have mass, but it's not in grams. Mm-hmm. It's in some other definition.
Yeah, it's curious. And the other question I had is for the laser model that you mentioned. How is it that the collimation of the laser beam can be very narrow and it can go extremely far without dispersing a lot, and yet it seems to be traveling through a gravitational field, which means a lot of G1s. So the G1 particles in the laser beam must be colliding with a lot of G1s, and yet it's not dispersing. It's not.
The peak of the laser has a lot of G1s, either clumped together or loosely flowing together. And yeah, incidental hitting is going to knock them away. And the number of G1s in the peak is the amplitude. So what happens in the case of those collisions, you just lose intensity. It knocks an individual one away and it's gone. There's less energy, less momentum now in that peak than there was before.
And finally, a suggestion for next week. Please describe the electric field between parallel plate capacitors, and then describe, if you would, the magnetic field within a long solenoid. Both apparently are G1 particles, and I'm trying to understand the difference between those two particular experimental setups. Parallel plates, what's the field in between? What's the G1 particles doing? And then as a long solenoid, what's the G1 particles doing in there? Because one is an electric field, one is a magnetic field. I'm not quite getting the distinction. So if you could describe that next week.
Between two parallel plates, in the particle model, the negative plate, the lower plate, gathers more G1s. The upper plate gathers fewer. G1s, by the way, go through a capacitor. They go through it almost anything. Most of them always go through. But you trap some here, a lot of them, and less here. What you create is a small G2 mass and a large G2 mass, meaning the electric force between is G2 gravity. Just like the gravity, G1 gravity pushing the moon to the earth, this is G2 gravity, G2 particles coming through that whole capacitor, setting up the reverse back EMF, if you will, is nothing more than G2 gravity formed between the charge between those two plates. Now,
obviously, I need to understand the G2 distinction a lot bit. So I'll go and think about it.
G2 is very critical. I got to hit G2 first to say anything about electronics, because almost every answer I got has to do with G2 gravity.
Okay. Well, I look forward to next week then. Thank you.
Okay, just let me make a few other comments, Bob. One of the things is it's when G1 particles are flowing through the universe, they're basically being blown out by suns constantly, right? Suns are blowing atoms apart all the time. So the suns are where G1s are coming from. But when you look at how many G1 particles at the speed of light you need for these things, they're not a lot. So when you just think, the way I picture it, the G1 and the G2 fields, is that if you take our intuition and I send our probe from planet Earth going out right now, like the Voyager, it's going out into space. What's its chance of hitting another Voyager out there or another comet? It's very small because there's so much space out there. When we look at this, even in a magnetic fields, even in a laser, if you look at that, the amount of G1 particles that gravity represents is extremely small. If you were to shrink yourself down to that level, it would be the same as comets. Comets, or we have rogue planets. We now know that there are planets that are not around suns. That would be like a G1 particle flowing. Now, do we see them coming by the Earth all the time? Do we see the Earth getting smashed all the time? This same space versus mass relationship. If you go down a level, now what you see are not suns, you don't see planets. What you see are nucleons and you see G1s. And this whole idea, I don't understand what G2 is. Well, G2 is the particle field at that level. So if you and I are pretending that this nucleus is a sun and this comet is a G1 particle, the reason it's curving around is you have a G2 field. It's going way faster than the speed of light because it has to. It can't hit something going at the speed of light at the speed of light. It doesn't make sense. So this G2, it's just like you go down a level, there's another particle level down there. It's like having a nucleon, and the nucleon's made of quarks, and then quarks are made out of these, and then quarks, those are made out of these. So that's the way I do it. I shrink myself down, put myself in space, and what you see as a laser going through space, maybe it could be something like a bunch of comets that are so far apart that we think they're not even together. But in reality, what happens is when those are like going and then they hit something, then that's why you don't have, to worry so much. Yeah, there are some collisions that happen, but it's not an immense amount because there's mostly space there, right?
And it doesn't
that
spread.
worries
It
me.
doesn't spread.
That worries me because I then don't understand how you maintain a curved path of anything, because it's so rare that you get an interaction or a collision with a G2 particle, because it's like the Voyager spacecraft going through space. When are you going to run into another Voyager spacecraft? You ain't.
Right,
So
because
how do you maintain a curve path if it's so rare? There's not a large density of these particles.
The gravity particle, G1 particle on the solar system objects are very large, okay? And so in our solar system, you can have, if you're going to, you got G1 particles all over the place. And if you freeze the solar system, one of the ways you do calculations is to assume that you've got 70 sextillion stars generating speed of light particles going through a solar system that's very large, moving very slow. So these particles are passing through at high speed, c, through a very small, and so you can have quadrillion, billions, whatever you want to say, interactions on a large object caused by a small particle moving at speed c. You get the same thing at a level down. You got an atom, a nucleon, and an electron, but you got a G1 particle field, G2 particle field surrounding it, moving at twice the speed of light or 10 times the speed of light. You freeze the atom, and you can have many of them passing through in a very short period of time, acting gravitationally on the object.
Okay. All right. Thank you very much. I look forward to next week.
Yeah. The other thing, Dad, too, is that if you look at it, I mean, one of the things that they say about even Mars, maybe those satellites were captured, right? We talk about that. In the amount, if you look at the thing that is hard to understand is the mathematical probabilities that are going on. The numbers are astronomical. When at that level, they're going so fast that what we are seeing could be literally an infinitesimally super small sliver of time where, it takes forever for something to capture something. But if you were to speed that up to 60 quintillion times, that is a lot less rare than one may imagine. So
one of the comments made by some of the other people has to do with the speed of the G1.
Yeah,
and we've kind of, in the particle model, we've generalized it. Often say it's like the speed of light, but it isn't necessarily a speed. So where does the speed come from? Well, taking a simple Bohr model, one electron, one G1 around one nucleon, it has a velocity. We don't question that where all these atoms came from, all the hydrogen atoms, they're out there. They're in the stars. They're combusting. They're being spread out. As soon as a hydrogen atom combusts and it releases the G1, it's going at a speed basically as it was orbiting. Now, G2 gravity can accelerate it, make it go a little faster. It can G2 drag can slow it down, so it can vary. So we call it C1. Speed is C1. It may be almost the speed of light. It may be faster than the speed of light. The irony is that when you go to a circuit, a battery emitting these G1s eventually gets to a laser that you got in your hand, and it spews out light that's moving at speed c. So it starts out in the battery as an orbital, and it ends up going out at speed c, which makes us think, well, yeah, it's kind of close to c, but it can be going faster or slower because G2 gravity can accelerate it or it can slow it down. So what is the speed? I don't know. We call it C1 because we don't know what it really is. But generally it feels like it should be close to C, the speed of light.
Right. One question is, why does light not travel less than the speed of light in your model?
It does.
Yeah, it does. And the thing is that I guess what the answer to the speed of light thing is what's really happening is G1s are being released somewhere by some atomic structure somewhere, right? A nucleon is holding these things, and now it's releasing them. And what happens is when it's released, it's out sort of in free space. And free space is basically, there's not like a lot of nucleons. It's not going to encounter a lot of things. The only thing that's out there is a G2 field, which is like, even the gravity field. And that's traveling at a much higher speed. And yes, it's called, it's, what do they call it? Inertia, right? And so you have these things hitting all the time, right? They're all hitting. So once they're in free space, they're going to pretty much stay at the speed of light in general. So, yeah. So that's part of the answer.
One of the interesting things about the speed of light being slower, I have a video on a redshift and tired light. If you ever get a chance, watch that, because I explained that the light coming from a distant star is subject to drag by the G2 field. G1 light is subject to drag. It's a gravitational drag, slowing it down as it comes towards you. Now, what that does is when it slows it down, it makes the spacing between the peaks bigger. It's slowing it. Well, no, the spacing is the same. The arrival time at your eye is longer because if it comes by fast, the time between peaks is short. If it comes by slow, the time between peaks is long. When it slows down, it makes the light do a redshift. That's the essence of what I'm saying in that, which means that the universe isn't necessarily expanding because G2 drag is slowing it down, causing a redshift, not because the wavelengths change, but because the speed fast, short time, speed slow, you get a longer time. And your eye detects the arrival time of the peaks, and that's what determines the color.
But so you're saying if you were to put a tag on them like they do with animals, and then you would tag it at one place and then measure it later, that wouldn't be traveling at the speed of light. The thing is how do we know? Because we can't measure the one-way speed of light, right?
No, that's what they say, yeah.
Yeah, so if you can't measure the one-way speed of light, how do we know that the light that the redshifted light's coming at us is at the speed of light?
That's the point. And I'm saying the model predicts it should slow down. The speed slows down. Therefore, you get an automatic redshift without the star moving away or without the Doppler effect.
Mm-hmm.
So it all speaks to the issue of what is the speed of this G1 as an orbital. What is it as it's going through space? If you always assume the speed of light is an absolute constant, you're going to get the wrong answer, because there's so many other things out there that can, whether we're right about the drag or not, maybe there's another mechanism that causes it to slow down. But they don't even consider that it can slow down. Light has to go at the speed of c. And I'm saying you don't know what that speed is in the orbital. And you don't know what the laser light coming out of your laser may not be at speed c, but it's red because the arrival time of the peaks hitting your eye tells you it's red. You don't know it's moving at speed c. Interesting.
Yeah. Okay, I've got somebody, James Keene. Hello. Okay, unmute yourself there.
Hello, thank you for your presentation. I'm wondering why apparently there are two and only two particles, G1 and G2.
No, there's the nucleon.
What led you to postulate the second G2 particle, and what distinguishes them? On a very elementary level, I'm asking this question.
Well, we have the answer. Let me get this get the slide up there. So,
my answer. My answer the first time, I'll tell you when I discovered it. I had taken the model for light that I came up with. This is not long after, very quickly after, in 2015, I applied it to a prism to study refraction. And the first thing I noticed when I looked at the bending of the light is that the forces required to cause the light to bend as it goes through, it comes in and it bends, is a force perpendicular to the edge of the prism. And then I noticed it also happened at the other end when it comes out. To make it bend the way it bends, you have to have a perpendicular force at the edge of the prism. And I said, I had been drawing forces around the Earth, like shown in that graphic, with forces perpendicular to the surface of the Earth. And all of a sudden, I'm drawing forces around the prism the same way. And I said, that looks like gravity. Except I'm bending light. I'm not bending Earth. I'm not bending moons. I'm bending light, and light's moving at speed c. How could I have a particle? This is a particle model. How could I have a particle that is bending light that only moves at speed c? It won't even catch up. You can't even catch up to the light. It had to move faster than c, and it had to act gravitationally with it in order to do a controlled bending. When you get a rainbow, you have controlled bending, just like when you throw a ball, it always falls the same way. When you shine light into a prism, you get the same rainbow every time. That's gravitational. And the only way you can bend light moving at speed c in a particle model is to have a particle that's faster than light.
And smaller. Yeah.
It's smaller. Where does that come? One last comment. Where does that come from? Where it comes from a subatomic. Only place I can think of it is there's a smaller atom, smaller nucleus, moving even faster than c, called speed c2. And when that particle is released, that's your G2 particle field. So that's when
why
I
you
came up with the
postulate
idea
a
that
second
there's
particle.
a second gravity.
And you mentioned nuclei or nucleons. How are these related to G1 and G2? Are the G2s in the nucleons, or what is the composition of the nucleon exactly? If I may ask, I'm really just trying to better understand you.
I get you.
Right.
The simplest analogy for me is that a nucleon is made up of 2,000 G1s. That may be totally wrong. It may be structured some other way. But that's one way to think about it, because it tells me why the G1 and the N1, when the G1 particle hits the nucleon and causes it to move, it's a collision. It's not gravitationally. That would be my first guess, but it'd probably be wrong. Ultimately, if you ever got down to it, maybe it's just a group of subatomic atoms thrown together in a big pile. I don't know.
We don't know. I mean, there's some. The answer is Universe Hack 3. We call our book Universe Hack 3 because we are really trying to solve the problem with light, gravity, magnetic fields, and electricity. That's a lot of work. That's hard, right? That's not. I mean, we're not like trying to do one thing. We're trying to solve many problems that, in our opinion, have never been solved or given physicality at all. We recognize very clearly that what we call Universe Hack 4 is to go down the one level and start looking at the evidence to see what we can see. Now, the only clue that I think that we've been able to see that has some really good hope is Jeff Yee's model of the nucleus. He doesn't have charge. He does have magnetic fields and he has electric fields, and those kinds of things in our model can be easily explained as a G2 magnetic field. Regardless, the answer to your question is we don't know. We solving those other big things, that's pretty amazing. If our model is correct about light, that's pretty amazing. If our model is correct about magnetism, that's pretty amazing. If our hack for what a rainbow is that even Newton couldn't come up with an idea about that's pretty amazing. To go down and do that next level, it's, in our opinion, if this model were to be looked at as a way to go, that's probably going to be 100 years. And so we don't know. That would be the answer.
Well, thank you.
Okay. All right. I've got something we'll talk about that's related to it, but we'll bring up Ian first. There is a talk about gravitational field and electric field. We'll get to that. Okay. Ian, hi. How are you?
Very well, thank you, David and Bob. Thank you very much. Most interesting attempt to unify the forces of nature into one particle. Just by the way, a trivial perhaps observation first is one might have called your tome Principia Mathematica 3, because sometimes Principia Mathematica 2 is given to the work of Whitehead and Russell of the second decade of the second decade of the 20th century. Yes, but anyway, my point, I'll be brief, is also related to the speed, and I know that you have indicated, particularly Bob, that the G2 particles vary in speed and they may be greater than G1 and so on, but I take it that this is fairly marginal. Now, David, you showed a slide where you were showing, things like, I think you had one slide where there was gravity and light during an eclipse of the sun, I think it was. And you were saying, experiments indicate that they're roughly simultaneous and so on. But yes, that's the very slide. So I'm just wondering, are you familiar with, or have you thought of, or do you counter the contrary work of Tom van Flandern, who indicated actually some experimental evidence, including during solar eclipses, that indicates that there's actually a delay between arrival of the two, the time of maximum optical eclipse relative to the time of the maximum alignment owing to the combined gravitational field of the moon and the sun, and there's a delay which would indicate that the speed of gravity is orders and orders of magnitude greater than the speed of light. Furthermore, things like electric fields and magnetic fields seem, well, there's some experimental indications of that, I don't have it to hand, but that they manifest themselves almost instantaneously. So again, very orders and orders of magnitude greater than the speed of light. And one further thing is Milnes has done some work some experimental work again to indicate that the current in a closed circuit, the closed current, is actually maybe hundreds of times the speed of light, not the speed of light. So I'm just wondering what your model has to say in regard to those experiments.
It's been a long time. I think Tom Van Flandern wrote a paper, What Do the Experiments Say? I think I had a copy of that quite a while back. And I don't know if it was in that one particularly, but he concluded the speed of gravity with various criteria, not just the eclipse, but other issues, that it could be 20 times the speed, no, 10 to the 20th times the speed of light. A huge number, frankly instantaneous, if you will. And of course, that's what Newton and Kepler and everybody thought back in those days. The speed of light was instantaneous. The speed of gravity was instantaneous. And then under those conditions, Newton's equation works very nicely. And all of that work is quite interesting. But the diagram that the first time I concluded that the speed of gravity was probably like the speed of light was when I did a paper on the Wang eclipse. Now, I'll grant you that the timing between where the gravity appears and where the light appears is slightly off, and that would give you some variation between the two, that if you actually had time to calculate it, you wouldn't get C for light and C for gravity. But the fact that it struck me as just looking at it, that these things, the gravitational force at your feet seems to appear at the same time the sun appears above your head when you're standing there at the ocean. So it seems like they're about the same. So I concluded very early on that it was probably C, but the real proof of all of that finally came in 2012. A group of Chinese experimentalists, that's the paper that they wrote, was issued in 2013, where they went very carefully, and actually, this is even hard, measured the speed of gravity between the moon and the Earth, because it's only at the speed C, it's only 1.25 seconds, and measuring that had to be hard. Paper's well written, and based on that, it sort of solidified. I've read it, and as I say, it's well written because they seem to account for the issues you need to account in order to come up with the calculation. And so with regards to other people who say it's infinitely fast, I really think in general today, we have to admit that the speed of gravity is C. General relativity, they say, because of the LIGO experiments, that the gravity waves were moving at speed C. Of course, that's the wave. Is that really gravity or not? But most people have come to that conclusion. And I'm convinced that as long as the speed of light and the speed of gravity are nominally the same, you can use Newton's equation just as we do today. You see the planet where it is, you mark its direction, you mark its distance, and you mark its gravitational effect, and it says they're doing it, their calculations, as if they're assuming it's all instantaneous, when in reality we know that they're both moving at, or I should say I'm agreeing with the issue that they're both moving at speed C. But people use it as today. I'm sure they do all their astronomical calculations based on assuming the speed of light is instantaneous and the speed of gravity is instantaneous, because it's easier. When you take the speed of light into consideration, well, shoot, it had to move by the time this got here, and so on. And people have objected that planets should fly out of orbit because gravity is coming from behind. You got all these crazy things, but if you work it out, I'm convinced you can show at the speed of light, whether, as long as they're the same, both half the speed of light, twice the speed of light, both instantaneous, you can use Newton's equation and get valid results as to the motion of the planets and whatever.
Well, thank you very much. I would just say, maybe in summary, that the very fact that we dissidents even have different views about this and indeed the mainstream, to the mainstream, would indicate that it's really a very important thing to establish. I'd like to have some very detailed series of experiments to establish this in a sort of an unambiguous way. And I would maintain that the reason these are not being performed, by general science, is that general science, they say, the science is settled. The theory of relativity says that the interaction of gravity is distinct from gravitational waves. The interaction of gravity travels at the speed of light. So there was no point in doing any experiments. I mean, they agreed with you, if you like, but although you're coming at it from another angle, I have a different view. And it's something I would suggest that maybe, David, we might look at trying to prompt further investigation on it so that it becomes clearer. But anyway, thank you for your views. It's interesting.
Yeah, the only thing I would say on that, Ian, is, and this is what I always come back to, and no matter what, I think it's a noble idea to look for the speed of gravity, for instance. The problem is then when we do find it, there's so much related to whatever model of the universe you think there is. I mean, it's some sense, what are we measuring? I mean, if you were to ask the average person on the street, they're going to say, do we know what gravity is? And we dissidents are going to say, well, we've got lots of ideas. We don't really know. But, if we know the speed they're going to say, if you know the speed, then what is it? And I think part of the problem that I see, and one of the things that has made this model so interesting, is that when you have a physicality for everything, you don't have the question of, when you find some data somewhere, what that means. That's a problem, because when you find it, then you're really back to the argument, okay, what is that? Is it the case that getting the speed of light will help if most of the world, 99.99% of the world, doesn't have a model for what even gravity is? And so I understand what you're saying, but I think that's an interesting part. Okay, I'll let it go.
If G1 particle is the cause of gravity and it's coming from an orbital that could be moving faster or slower, how do you tie down the average speed of particles that are slowing down, speeding up? How could you make it absolute and give it a finite number?
But I can understand. I think what we can do is we can look for more evidence for speed of gravity, for sure. But in the end, you're still having to say, what is the heck is gravity?
Yeah.
Right?
If you could nail it down, that is absolutely the electron is going around the hydrogen atom at exactly the speed of light, and it never speeds up and it never slows down. Yeah, now you could talk about an absolute precise value.
Because I know. Go ahead.
The only reason that is useful to have an absolute definition for the speed of light is because there are test instruments. My scope in there, when it receives an AC signal, assumes precise speed of light to tell you what the frequency is. And if your scope does it differently, then we can never agree on results. All the instruments that work with signals that are working at the speed of light have to use an absolute number, the same number, even if it's wrong.
Yeah, and I do think Oh, wait. I'm gonna have to add you. Go ahead. Say that again.
Quickly. It's one thing to say that the speed may vary somewhat, and that's been discussed. But I mean, for one set of evidence or one set of argumentation to say that it's 10 to the 20 times one value, and the other set of experiment, the Chinese paper you gave on the tides, to say no, it's equal to it. I mean, that's one heck of a difference, and we should be able to discriminate between the two.
Sure. No, I agree. I agree.
Yeah, you need to go back to Tom Van Flanders' paper, find out, get his basis, get his data, and reinterpret it with your ideas or with our ideas, and see what we come up with, if we can resolve the difference.
So maybe we'll look at that in the future. It might be one of the projects.
No, I agree. I think part of it is, I remember reading that book. Dad, you stole that from my library. I remember one time I was at your house, and it was like what was it called?
Pushing gravity.
Pushing Gravity, and it was it was a book, and I had read it, and I will tell you my impressions, because it's been such a long time, was it was mostly anecdotal evidence, in my opinion, for what Tom Van Flander was saying. So I didn't come away with, and I have to go back to the book just like my dad. It's been a while. When I read it, I'm thinking, yeah, it's not like an experiment like that paper that my dad found, or the other one for the Wang eclipse. So that I would say. But my dad took that and read that, and I remember that was one of the things. The other thing too is that there are a lot of etherists that talk about it as almost being instantaneous. You know who says the word instantaneous, which doesn't make any sense? Borkert. Borkert says that gravity is an instantaneous thing that has to do with the entrained ether. And it's funny because he's a person that would be the last person to say anything in the universe would be instantaneous. But you're right. I agree, Ian. I think what we need to do is maybe, Dad, we can go back and take a look at that. That'd be an interesting just to talk. It's just to look at pushing gravity and look at the evidence in it and have it as a discussion thing, right? I mean, that would be quite interesting. So, no, I see your point. Thank you so much.
Thanks,
Ian. Okay. But another thing, Dad, that was interesting was this one here. People... This is where, again, I was talking about, because we're going over, but we'll go over a little bit here. One of the things without a model, you don't have a model. You don't have a model for gravity. You don't have a model for electricity. You don't have a model for a magnetic field. None of that. And then you start talking about gravitational fields and electric fields, but a person who says those things doesn't come to you and says, this is what it is, right or wrong. I mean, our model says this is what a gravitational field is. And the problem with, I think, Dad, I don't know if you would agree, the problem with the terminology of gravitational field, electric field, charges moving charges, creating fields, affecting moving charges, is all of that lives in a world where there's no physicality. None whatsoever. It's what Alexander Unser talks about, arbitrary packages with arbitrary attributes. So we talk about those. We give mathematical equations for them. But when you ask them if it doesn't matter, we still have to answer these questions. Yeah, but if you look at our model, you don't have that. What you see when I see a gravitational field, electric field is, my first question is, what's your model for that?
By the way, G2 is a gravitational field.
Right.
Nothing in our model is electrical. And I know the EU people don't like it. They don't like it when we say there's no charge. But our model is totally mechanical and gravitational. So you got yes, I can say it's equivalent to the electric field in certain cases, like inside a battery, inside a capacitor. You can say that, but we're describing it literally, functionally, mechanically as a gravitational field.
Right. I mean, one of the things we don't have in our 4 classification is ether, which is the bouncing of particles and back and forth, and so we can describe it. Anything that curves, anything in our model that curves, is caused by random particles going in straight lines. That's what we say. If there's a curve going on in some level of the universe, whether it's a comet curving around a sun or an electron curving around a nucleus, it's going to be caused mechanically in a Newtonian world by particles going in random directions and in straight lines. That's the essence. That's why at the beginning of our book, on the cover of our book, we have that. So I guess because we've come up with a lot of, we've gone over our time, we're going to go into next week. We'll accept people's definitions for our contest. That is, if you have described the particle model in your own words, we'll be giving that. We'll be collecting those. You can send them to our email, david@dhilster.com, bob@dhilster.com. Just use our first name, last name. It'll get to us, and we'll consider that, and we'll be giving that. So next week, Dad, you're going to be talking about the particle model when it is applied to electronic circuits, right?
Yeah,
and
that's a big subject, and I'm not so sure in 2 hours that I'm going to be able to explain everything anybody wants to. So I'm going to try to keep it to a simple RC, not RC, a simple battery resistor and an experiment. And then I'm going to talk about the second experiment where I use the speed of the G1, how the speed of the G1 actually affects the performance of a simple DC circuit. Those are my two experiments. I think highlighting those two experiments next week and the giving enough of a background so people understand why I'm doing the experiment, what I'm looking for those two would be good, because those experiments give supporting evidence for this model. Current around a circuit is not identical.
Right.
But
And that's
Ohm's law says current is the same all the way around the circuit. This model shows it predicts it's not, and I've done the two experiments that show it's not. And I think that's important. So we have supporting evidence for the model, because I can show you, David says he's going to show you my lab, my elaborate lab. And
cardboard table.
I think that'll help be really convincing that maybe there is something to the model. There is supporting evidence. There's no proof that it's true, but these two experiments give supporting evidence, which I think is quite astounding.
Yeah, that was pretty shocking. I think the biggest thing before we go, I know again I'm running over, but I think one of the things when I talked to my dad about, applying this to electronic circuits, I said to myself, inside me, right? Because I'm the biggest skeptic on anything, even on our model. I mean, I'll wake up one day saying this model's this is too simple. It can't be this way. And then in the same day, I said, wow, this could be really something. So, but one of the things I said to myself was, if what we're saying about these four movements, gravitic, luminic, magnetic, and all those things are really going to be worth something, what happens when an electrical engineer who spent their entire life as an electrical engineer, pretty successful one in research even, applies this to electronic circuits? Is something going to happen? Is a person going to look at electronic circuits differently? And the acid test was my father, and amazingly so. And if you look at, of all the technologies that humankind has come up with, all the technologies, whether we understand the physics or not, electronics is the biggest technology that, in my opinion, it's the most important technology we have come up with in the human race. It does more for us than anything. And to actually have physical explanations for it where we don't have any idea what this physics is, and it's been great. And he's come up to me and said things that I didn't believe. It's like, oh, it's speeding up and slowing down here. I go, it can't be that way. And it is. So in our model. So I'm just saying to everybody, look forward to next week, my dad talking about the application of the particle model to electronic circuits, some predictions made by the particle model, and actually confirmation that these predictions seem to be true, that electrical engineers have not even considered, which is quite amazing. Is that correct, Dad?
It's quite amazing. It shocked me. Oh, wait a minute. That's electrical. I'm sorry.
Okay, folks, so we're gonna go out here, but thank you so much, Dad, and we're looking forward to your talk next week.
Thanks for everybody for showing up. I appreciate it.
Yeah. And again, thank you so much. I want to thank if you haven't hit subscribe, hit the subscribe button, please, guys. That helps us if you aren't into it a lot, but want to see more things like this. We have lots of different models. This is just one model that people have come up with. It just happened to be my father and I's model. We have great people on. Next week, we're going to talk about electronic circuits in a particle model. After that, we're going to talk about quantum mechanics, the history behind that. We're going to have some debates. We even have suggestions for new topics like the speed of gravity. That's a whole other subject, evidence for that. So I want to thank everybody. I want to thank all the CMPS members. And again, hit the like button, hit subscribe, and become a member if you can, and support this. All the monies go to it. I want to thank our super chats, people who you can send through YouTube money. All that money collected will go into our CMPS bank account that spends about $2,300 a year to keep this going with video, our websites, and all those kinds of things. Doesn't pay anybody. It's all volunteer work. So I want to thank everybody, and let's head our way out. And remember, stay critical, stay thinking. I'm Dave D. Hilster. I'm your science therapist trying to get you to the promised land of becoming a critical thinker. Think on your own. Let it roll around your head. Don't believe everything everybody tells you, not even me. Check it out yourself. Ciao for now.